Hi, and welcome to Module 10. This is on air pollution. This is Sarah, and I'll walk you through a few slides to review some of the important concepts that are outlined in Chapter 13. So air pollution has been recognized as a threat to health for thousands of years. It sounds pretty amazing, but even thousands of years ago, scientists noticed that when coal was burned, people would experience adverse health effects. Back in the 13th century in London, the air pollution was very bad. And again, this was from burning quite a bit of coal, which we've had a history of doing. In modern times, there have been 3 episodes that are summarized in the text, the most notable of which was in London in 1952. It was a very cold winter, there was a lot of coal being burned, and there was also a temperature inversion, which is where the clouds trapped a lot of the pollution down into the city and wouldn't let it move around. And this incident was associated with thousands and thousands of deaths. In 2010, it's estimated that air pollution attributed to 3.2 million premature deaths, which is really a lot of deaths. Air pollution is a very serious health hazard, a health risk, because everybody has to breathe. It's a little bit unlike water. If your water is contaminated, you can drink some new water, or you can filter your own private water, but it's very difficult to control ambient outdoor air pollution. When we talk about the types of ambient air pollutions, it's important to understand that the pollution, whichever contaminant you're talking about, the concentration in the air is dependent on several factors, including the emission. So if it's a pollutant that's being emitted from a chemical factory or from a fossil fuel burning factory, it depends on how much is being emitted. It depends on where it's being emitted. How high is the stack where the pollutant is being emitted? If it's emitted low to the ground, it will stay in that lower atmosphere where we can be exposed. If it's emitted higher in the atmosphere, we might not be exposed to it immediately, but then it can travel around the world easier and expose other people in a more diluted manner. Weather and land patterns are also really important. When there are temperature inversions, when there's a lot of thick, muggy weather, you can experience a lot higher level of air pollution. Stagnant winds will also contribute to a high level of pollution. And of course, the air pollution can vary by season. A good example is here in the New England area. We burn a lot of wood when it gets cold outside. So in the winter, we have a different type of air pollution than we have in the summer. So some pollutants can travel large distances. This can be impacted by where in the atmosphere the pollutant is discharged to. We can also categorize ambient air pollutants by their source and their chemical characteristics. So the first way to characterize them is whether they are primary or secondary pollutants. So primary pollutants are emitted in their current chemical form from the source, whereas secondary pollutants are formed from primary pollutants and other reagents. Secondary pollutants are formed by a chemical reaction. We also think about whether the source is biogenic, such as natural sources, things like plant decay, volcanoes, or whether the air pollution is caused from anthropogenic activity, that's human activity, such as burning fossil fuels or driving cars. We also think about air pollutants in terms of regulation. So there are 6 criteria pollutants which the U.S. regulates. We'll talk more about these in the remaining slides. These are carbon monoxide, lead, nitrogen oxide and nitrogen dioxide, ozone, particulate matter, sulfur dioxide. And there are also hazardous ambient air pollutants that do not have these national quality standards. So the next 2 slides will talk more about some of these these 6 criteria pollutants. And these are tables that are taken from your book. The first one that we'll talk about is lead. It's important to note that this is a primary pollutant. Lead is emitted as lead from the burning of fossil fuels and also from leaded gasoline. It's also emitted from processing plants, and this is as a result of human activities. This is anthropogenic. Sulfur dioxide is also a primary pollutant, which is emitted from combustion of fossil fuels as an anthropogenic source, but it is also emitted from decaying organic matter, so dead plants and dead trees, and this is a biogenic source. Carbon monoxide is a primary pollutant. It's emitted as carbon monoxide, and it also has both anthropogenic sources and biogenic sources. Particulate matter is the next category, and unlike the other 5 criteria pollutants, particulate matter doesn't have a specific chemical formula or chemical structure. Particulate matter is the total association or the total amount of all the particulates that are in the air at that time. Particulate matter can contain lots of different chemicals, and it's going to be different depending on what part of the world you're in. And particulate matter is grouped based on size. So that's the biggest thing about particulate matter, is the bigger particulates have less chance to get down into your lungs and harm you, whereas the smaller particulates can really get into your lungs and cause adverse health effects. Particulate matter is both primary and secondary because it is so varied in chemical structure, and particulate matter is also found from anthropogenic and biogenic sources. Nitrogen oxides, that includes nitrogen oxide and nitrogen dioxide. Those are both primary and secondary pollutants created from fossil fuel combustion as well as the biogenic sources. And then we have tropospheric ozone. This is a secondary pollutant, so ozone is not emitted from a chemical manufacturer or from burning fossil fuels. It's formed through a chemical reaction of precursors, some of the precursors that we've talked about, as well as the volatile organic chemicals and sunlight. So when we think about air pollution and the health hazard, it's important to understand not only the physiology of the lung, but also to understand how a chemical's properties can cause it to be more harmful or less harmful to your health. So the toxicity of a particular pollutant is definitely affected by its physical form and its chemical properties. When we think about a chemical like sulfur dioxide is very water soluble. So when it's breathed in through the nose, it gets dissolved in the nasal cavities, and it doesn't make it down to the lungs very much. That can be different if it's a very bad air quality day, and if someone is outside exercising and breathing very heavily. If someone's running and breathing through their mouth, then they're likely to get more air. They're breathing more air, first of all. But by breathing through the mouth, you're giving the chemical a more direct pathway right into your lungs. So it's definitely better to breathe through your nose so that your nose can filter out more of these ambient air pollutants. And when we think about pollutants like particulate matter, in this diagram, you'll see at the very bottom, particulate matter can get down all the way into your alveolar sacs. And when very, very fine particulate matter gets down that deep into your lungs, that can cause a lot of long-lasting health effects, specifically respiratory effects. There have been a couple of really important and really impressive air pollution studies that have been done to document the link between air pollution and adverse health outcomes. When epidemiologists conduct these studies, they often use ambient air monitoring data. So a lot of states, or most states, all states, have air quality monitoring stations set throughout the state. In Vermont, we have one in Burlington, Rutland, and Underhill. And these air quality stations monitor the ambient air for the 6 criteria pollutants as well as several other air pollutants. And it's very easy for epidemiologists to use that level of the ambient air from the monitoring stations as a surrogate for individual exposure. If we think back to our modular exposure assessment, it can be very difficult to monitor hundreds of thousands of people for their individual air exposure. So a couple of studies that are summarized in the text are the study from 1993. This study looked at 6 different U.S. cities and looked at their air pollution levels and showed a 26% higher mortality rate in the city with the highest pollution versus city with the lowest pollution. That's a really big difference. Another study that's a little bit more recent was conducted in 151 different urban areas, and this study found a 17% higher mortality in areas with the highest versus lowest air pollution. Sometimes human studies are conducted to understand more about the disposition of a chemical within the lungs, but if studies are conducted on humans, they're often very short durations and very low exposure levels. It's not very ethical to give human volunteers large doses of air pollutants that would cause health effects. It's more common to see health studies done in animals or in cells or simply in test tubes. So here's a slide that just gives you another diagram, another look at particulate matter. So again, particulate matter is the category of pollution that is based on size. It can be an assortment of various particles, including the 6 criteria pollutants that we've talked about, and they are measured by size. And so when you see PM10, that means particulate matter that is 10 microns in diameter and below. When you see PM 2.5, that's particulate matter that is 2.5 microns or below. PM 2.5 is well recognized as a health threat. That was the most recent one to be added to the list of pollutants of concern. And more recently, there's been discussion about ultrafine PM, which is 0.1 microns and lower. That's the next frontier of air pollution. So a bit more about the tropospheric ozone. So it is a gas that's found in the lower atmosphere. That's the troposphere. That's the air that we're breathing. If it's found in the stratosphere, which is several kilometers above us, this is the good ozone. This is the ozone layer that protects us from the sun's ultraviolet rays and prevents cancer. But the tropospheric ozone is a secondary pollutant formed by chemical reactions of the precursors. Much like the other air pollutants, the concentrations can fluctuate in the hot and cold months. The levels of ozone are often lower indoors because ozone is a very reactive molecule and it sticks to basically every surface. Because it is so reactive, it can cause a lot of damage when it gets down into those alveolar sacs. Ozone is not water soluble at all, and it is very small, so it can get down into your alveolar sacs quite easily and can damage lung tissue there. And it's been shown that the high ozone days are associated with increased asthma attacks, hospitalizations, and even mortality. The last slide here is on air pollution prevention and control. There's various approaches from controlling emissions at the source, so that could be regulations that allow a plant to only emit a certain amount of an air pollutant. It could also be a scrubber, which is an air filter. You can imagine it as a Brita filter that's in the emission stack of a plant, and it absorbs all the chemicals that are going out. You can also control exposure. This is both the state and EPA offer advice on air quality. So if you're a person that's very sensitive to air quality, such as a young child, an elderly person, or someone with asthma, it's important that you watch for those air quality alerts and avoid going outside for too long on a bad air quality day. The U.S. Clean Air Act was established in 1963 and updated in 1990, and that's a legislation that established the NAAQS standards for those 6 criteria pollutants that we've talked about. They also have secondary standards, and they also have maximum achievable control technology to reduce other pollutants that don't have NAAQS standards. When geographical areas exceed the NAAQS standards, those are called non-attainment areas, and then states are required to develop implementation plans to get those air pollutions back in control and below the NAAQS standards. One method that's often used is the power plant cap and trade. So plants that emit too much sulfur dioxide can buy credits from plants that don't emit their share. We don't have that in Vermont because we don't have fossil fuel. We don't burn fossil fuels here in Vermont on a large scale. So thank you for listening. I look forward to the discussions.